The morning talk is by Professor Girolami from the University of Warwick, who's going to talk to us about Bayesian uncertainty quantification for differential equations. Thank you very much.
Thanks, Dan. And thanks, everybody, for getting up so, so early to come and hear this. This is relatively recent work, and it's joint work with one of my former PhD students, Ben Calderhead, who's now at Imperial College in the Maths Department as a lecturer, Oksana Shredti, who's at the Statistics Department at Ohio State, and then Dave Campbell, who is at Simon Fraser University in the Department of Statistics.
Who's the little boy?
Sorry?
The little boy is in the team as well?
The little boy? Yeah, it's, yeah.
No.
Oh, him, yeah. He's the lead author.
So that's Mark Girolami, what is it?
Yeah, that's. I bet you didn't recognise it. And this work, this whole notion of trying to quantify uncertainty in the overall modelling process of physical and natural systems is a long-standing theme in my own personal research and forms part of a programme of research that's based at Warwick and is led by Andrew Stewart on, surprisingly enough, enabling quantification of uncertainty, specifically for inverse problems. Okay, so let me just give you an outline of what I'm going to try and do today. And the first thing is to try and motivate why we would want to quantify uncertainty in the mathematical modelling and subsequent computer simulation process. So we want to do this all within a statistical framework that allows us to coherently make inferences about objects of interest once we've observed some data. The whole basis of this work is to acknowledge that solutions of differential equations, be they partial or ordinary, and all of the varieties of partial and ordinary differential equations, is that for all but the sort of simplest and most trivial model equations, there is going to be an infinite and finite dimensional mismatch. So typically, to simulate or to solve a system of differential equations describing some natural phenomenon, then we have to recourse to typically a numerical integrator, which is in essence finite. And therein is the source of uncertainty that I'm going to focus on today, is this mismatch between the infinite dimensional functional representation and the actual finite representation of a global solution of the system of differential equations, which is based on some sort of finite mesh or finite grid. And the overall goal of this work is to obtain a posterior measure for the uncertainty in the solution. Now, of course, mathematically, well, in terms of numerics, we can obtain bounds on errors based on a particular discretization strategy. But here what we want is an actual probabilistic statement about that error so that it can be subsequently propagated through the overall inference process, as you'll see shortly. And so what we're proposing here is a scheme of, rather than a deterministic integration, is a probabilistic integration in a way that constructs this measure over the solutions of the systems. And what it allows us to do, in essence, is sample from this measure actual realizations of functions which will or are consistent with the constraints imposed on them by the system of differential equations. Now, of course, this is somewhat different to the approaches that are taken using, say, Feynman-Kac equations where you could solve certain partial differential equations locally by taking an expectation of, say, the boundary functions with respect to the law of some associated stochastic differential equation. So what we're doing here is we're not so much interested in local solutions and local measures of uncertainty. We would want global ones, because the sort of problems that we deal with in inverse problems are such that the parameters, so say Navier-Stokes or what have you in incompressible flow, unknowns like the viscosity would actually be non-homogeneous and would be distributed. And so I'll give some examples of ODE and PDE systems, and quite a big illustration on protein dynamics, and then conclude and discuss some of the shortcomings and work that still needs to be done in this particular area. So just in case you didn't read the title of the talk, this is taking a sort of Bayesian approach to probabilistic uncertainty quantification. So, just to remind you that in a system of differential equations, the derivatives with respect to either spatial or temporal variables are related, and they're related implicitly. And this is the key thing, is that this implicit definition of the states of interest, so some property u given some spatial variable and some time element, is defined implicitly via this sort of scheme here. So here's a very simple initial value problem where you have the time derivative of u, and it's linked to the actual states via some nonlinear function which describes the derivative field. And then we have an initial condition to ensure that there's going to be uniqueness of a solution. And there are a whole lot of variants of this thing here. So I think the key element, the key difference here is that because this is implicitly defined, then this is a source of uncertainty that we have to take account of. And I'll get on to why this is actually quite important later on. For PDEs, of course, there are three classes of different types of PDEs. Here's the sort of standard one that we all learn in, I don't know, PDEs 101, typical parabolic PDE defining the second derivative. So I'm just keeping things very simple. Everything is just going to be written in 1D, but everything extends to multiple dimensions, multiple variates. So again, the system of equations implicitly define the solution, so the actual state that we're interested in. And therein, I argue, is a source of uncertainty. Now, of course, for this is a very simple model. It's one where solutions are analytic and so forth. So this is just for illustrative purposes. But I'll be talking about things like Navier-Stokes later on, which are somewhat more challenging than these little examples. So of course, from a statistical perspective, we now observe some data. So we make some measurements, we gather some evidence, and we have this data, which I'm just calling y of t. And again, I'm only, just for presentational purposes, I'm not going to be talking about spatial components as well. But again, all of this holds for ODEs and PDEs, nonlinear systems. But just to keep notation simple, just so that the ideas I can get the ideas across, I'm just going to focus on time. So we've made some observations, we've got some data, and we have a mathematical model which we place some trust in to describe the phenomenon of interest, and there are a set of unknowns that we would like to perform inference on. So I'll just call these theta. So these could be parameters, these could be initial conditions, boundary conditions that aren't known, and so forth. So if we were able to obtain the exact solution of the mathematical model, which we'll just represent as U star, the sort of classical, very simple observation model would be such that we would tie the data to the solution, right? So the states of the solution of the differential equations, and we would have some observation process, noise process or error process, depending on the instrumentation that we've used. This could be multiplicative, whatever. But again, just for the purposes of this talk, I'm going to consider it as additive. Now, there was a landmark paper in 2001 where Mark Kennedy and O'Hagan defined the framework which really allowed someone who was studying systems like this to say, well, I have my mathematical model or my computer simulation of the mathematical model. However, I believe that there is going to clearly be some sort of mismatch between the physical process and this model. And I can account for that by adding this sort of random variate term here. And in their paper, they employ a Gaussian process to capture this inadequacy of their model, or the inadequacy of what they claim to know about the process. So this in essence is defining the mismatch between the mathematical representation and the actual natural or physical process itself. And they give some very nice examples of gas plumes diffusing after nuclear accidents and so forth. So there now, immediately, we are acknowledging that there is uncertainty in the model itself. So if we now want to start to employ the statistical machinery, the very first thing that we need is a likelihood. Probability of our data conditional on everything. So the solution, parameters, and other variables that are of interest. But the key point here is that we can't get this likelihood because we can't obtain this object here. Right? We can't get this function in most examples of interest, and that are not trivial. Now, standard practice in applied mathematics, in engineering, in physics, statistics, would be that we would just replace the likelihood with a surrogate, which is now conditioned on the n-dimensional finite representation of the solution states. So this could be, as I said, from some finite element program, what have you. But at the end of the day, we are now conditioning our data on a finite representation of this infinite dimensional object. And the accepted wisdom and accepted practice has been that we just use all the compute power we can to drive the error of this finite dimensional object down to something that's absolutely negligible. And for a lot of nonlinear ODE systems and certain PDE systems, this is fairly straightforward. However, one of the interesting things is that we are bombarded every day by claims about big data this, big data that. But one of the things I think that's really exciting for statisticians is that we are in a regime where we have big models. So I'm working with people in Texas who are geophysicists, and driving the error down for solutions of models of ice flow, in the polar caps, is not a straightforward thing. And even characterizing that error is not a straightforward thing at all. And so, again, the sort of standard practice of just running a solver until the error is negligible, for a lot of problems and a lot of big problems, this is not something that is always feasible. And what I'll show you in a very simple example is that this assumption of negligible numerical integration error can actually lead further downstream in an inferential perspective to really serious statistical bias. And I'll give you an example of that with one of the simplest of PDEs you could imagine.
Sorry, the capital N is the number of observations.
So capital N, yeah, I beg your pardon. So capital T is the number of observations of data, right? So, and capital N is the number of integration steps in solving the ODE, or capital N is the number of grids, the level of meshing in the PDE solver. Okay, so this is just there to remind us that this is an approximation, and it's a finite dimensional approximation to an infinite dimensional function.
And as n gets larger, you get an arbitrarily good approximation?
Yes. So in the engineering literature, in fact, the two forms of uncertainty are called validation error corresponding to what Kennedy and O'Hagan and statisticians would call model mismatch, and verification error, which is this error that I introduce here, which is in essence the error between the desired solution and the finite representation. So this would be the verification error. And so a lot of work is done in trying to characterize bounds, error bounds on this error, and then use those bounds to make decisions as to whether a finer mesh is required or what have you. But what we would like is just to have a probabilistic statement about the uncertainty associated with this discrete integration process. And so in essence what we do, if you think of Kennedy and O'Hagan's work, they basically assume that they know from a certain number of simulations or runs of the computer codes what the inputs are and what the outputs are, and they basically define a statistical model just based on a Gaussian process of the system. And it's completely agnostic to the underlying mathematical representation, and it's and what we do in this work is we basically say, well, because there's an underlying mathematical representation, then we might as well use it in trying to characterize the uncertainty, statistical uncertainty associated with this. Now, the way that we do it is we now consider approximations of this as basically a stochastic process. Now, when I've given this talk to numerical analysts, they immediately jump up and say, but hold on, there is no stochasticity in solving a system of differential equations. We know the functions, there are functional representations for the error, there are functional representations for the error rates, we can actually write them down. So where is the stochasticity? And the key thing here is that from a statistical perspective, a bit like Rumsfeld, there are known unknowns. Right? So we know that our model is a mismatch to the natural, the physical process in some sense that we don't really know, but we want to capture that. And likewise, here, we have bounds, but we don't have actual access to the real error. So again, we have another sort of unknown. And this gives us, this presents us with this notion of epistemic uncertainty that we would at least like to take account of, so that, as I said, throughout the inference process, if that epistemic uncertainty due to the numerical integrator is negligible, then there would be some measure that would collapse to a point mass, and we would know, we would be able to assess the impact of decisions about the type of solver or the how much we would refine the mesh and so forth, in a probabilistic way, in a statistical sense. So in essence, this is what we do. We replace the finite dimensional representation by this stochastic process here. And we now, from a Bayesian perspective, we now change the object of interest from what would have been pi theta, all our variables of interest, given the data and whatever else, to pi of theta and the actual unknown function, which is consistent with the system of differential equations. And then we're going to have some additional hyperparameters because we have to introduce a statistical model to define this uncertainty.
Is stationarity an assumption that we're making that doesn't necessarily by default applies when you do
What do you mean by
of the
stationary?
Gaussian process?
No, we're not making an assumption here. We don't make that assumption. And it's not a necessary one.
Sorry, what is psi?
So psi, you will see psi. So in essence, what we are doing, we are defining, so we have our prior based on all of the unknowns of the system of equations. We have the likelihood, which is a thing of interest. And then we introduce this model of the mismatch between the stochastic process and the actual solution, and there are going to be a set of parameters associated with this. So that's all these are. These are the sort of hyperparameters associated with this second level that we introduce into the statistical model. So I've just said that we want to do posterior inference over those additional hyperparameters as well. And so now, if we write out the target of inference as this here, we now have a means of assessing, we can get the marginal distribution over either the variables of interest or the actual functions themselves. And what you'll see, what I'll demonstrate is that by defining this posterior, it allows us to actually draw realizations of these functions. And so for systems that are chaotic, or like turbulent flow models of Navier-Stokes, then the natural variability, the natural uncertainty can be captured by repeated sampling from this measure, rather than considering it as a deterministic solution obtained by integrating over a grid. You buy that? Good. So the next step then is really to, how do we construct this measure over these functions? And that's what I'm going to talk about now. So again, we are now modeling this as a stochastic process. So we can define a kernel. We could in essence just write out u of t is just equal to some convolution with respect to some kernel function and some white process. Okay, so very standard. So if we define some deterministic kernel function which has like a length scale, so this lambda and other parameters would all be looked at, would all be thrown into this psi variable that you asked about, Dan. So we can define the integrated version of this kernel just in standard ways. And what it now means is that we can define a covariance operator quite simply. So here's a covariance operator between the time derivative of the states, and this is going to be positive definite just by definition or by construction. So we just integrate the two kernel functions, and I'm going to represent the overall covariance just as RR to denote the covariance between two time derivatives. And alpha is a prior precision parameter. The covariance on the state, well, it's just going to be the integrated version, which again I'll just denote by QQ. And cross covariance terms between derivatives, state derivatives, and the actual states themselves are defined in a similar manner. So we can then obtain a Gaussian prior jointly over the time derivatives in this case and the states, just in this simple form here. So we have these covariance operators, and the important thing here are these cross-covariance operators, because you can now see that we've got a probabilistic mapping directly from the derivative space to the actual state space itself. For PDEs, we just go through the same mechanics. And so here's an example of the covariance that we could construct with respect to second spatial derivatives. And again, there would be decisions that would have to be made as to the form of the covariance operator. Here I'm just taking the most simple-minded, which is just a product form. So the covariance between these two second derivatives would just be the standard kernel over space, and then the integrated form over time. But there could be a whole load of other options that could be used there. And likewise for the covariance between the states. And so for a very simple parabolic PDE, then we would just simply have a Gaussian measure which would have covariance structure that looks like this. So tying second spatial derivatives with the time derivatives and then the actual states themselves. Okay, so that's the measure over the functions and all of their various derivatives. Now then, let's construct this model of the actual solutions. So the first thing that we need to do is we need to define a discretization grid, right? And again, I'm only talking about time points, but this holds for meshes in space and time. So we've got n time points, S1 to Sn, on some interval. And the construction is as follows. Let's fix the initial value, which has been given to us, right, at one of the extremal points, and we'll compute the exact derivative. So this is just a very simple initial value problem. As I said, this holds for all manner of PDEs, but just to keep things simple and just to get the idea across, I'm just focusing on an initial value problem here, where the time derivative is some nonlinear function of the states. So we can take the initial value, right? We can define that obviously as the state at the extremal time point, and we can then plug this in to define the vector field at the first time point, right? So this would be our time derivative at the first time point. And this is all deterministic, of course. So now what we can do is we can then take this and we can update the GP prior given the exact derivative f1. And this just gives us a conditional predictive distribution for the state at a subsequent time point, either forward or backward if it happens. So we can now define the probability of the state at S2 given f1. So this is the vector field defined by the states at S1. And it just turns out that this is a conditional Gaussian measure where the conditional mean it just follows the standard forms, the conditional mean and the conditional covariance. And again, if you just look at this, you can just see, well, we know that this is the functional of the time derivative, and we now have a projection from the derivative space right through to the state space. So we're doing this integration in a probabilistic manner. So we can then use this to sample a realization of the solution state at time point 2. So that's what we do. We just sample realization of the state at S2. And then again, we can link the prior, the ODE, right, via the sampled value of S2, and that then gives us our derivative. Now, of course, in this case, f of u2 is not going to be exactly equal to, it's not going to satisfy the system of equations, and there's going to be some error. And we model that error simply by the predictive variance at the second time point of the derivative process. So we augment this vector, so we've got the vector field representation at the first time point, we've now got it at the second time point, so you can see that we're going to start to build up this vector f at each of these time points. And we then define now our predictive distribution over the third time point, conditional on the previous ones. And these means, again, just follow the standard form here.
Do you need all the previous ones, or just need?
No, you don't. You don't need all of them. What we've done here is we've just written it in such a way that you can have them all. But the proof of consistency then require the proof of consistency is such that even with all the previous time steps for certain conditions, this will give us a consistent estimator of the actual states of the system.
But the way you define R and all the others, you just use the last one, don't you?
And here we could just use the last one, or we could use all of the. So here what we're doing, you can see that we're now using the last two time steps and state function.
Right. But when you define the R and all these things, you just go from S2 to S3. You don't go back to S1.
No, we in this case here I'm writing it out that we go back to S1. So in essence, so rather than saying, what happened here?
It's supposed to do that. When you put the thing back down, it'll come back on.
Oh, right, okay. So here, we have QR, which is now going to be at S3, right? And then this is going to be conditional S2 and S1. So
What is that? Because you are only define it from S2 to S3.
say that again.
When you define the R and integrate it, you only had it from on an interval.
Ah, yes, but this is now defined. I see what you mean. Yes. Yes. So here, okay. So here I'm, yeah. In this case, I'm now assuming that the interval is infinite. But for the case where I've defined here that it's only a finite interval, then yes, we would only, all that we would be using for S3 would be the S's associated with that particular interval, which could just be one. Yeah? Yeah. Okay, so that's the basic construction, is that we sample from this conditional. Given the sample of the solution, we then augment this this vector, which is obtained by plugging in the sample state into the right-hand side of the system of equations, if you will, and then continuing on in this fashion here. And what this eventually gives you, so what I'm describing here is the predictive state mean and variance at point n plus 1 conditioned on 1 to n, and we can then just sample either step ahead or step behind or what have you from this predictive distribution. And what we end up with, what we would return, would be the overall solution, derivative solutions, plus the associated measure on the function u. So this is the key thing, is that we obtain a joint distribution over u at any arbitrary t, and this particular realization of this overall process here. Okay, so we get a p of u at some value t and f. Right? So that this here is the mean and covariance structure of the conditional of u conditioned on f, and then we're also going to have some probability for this evaluation here. The key thing is that we can actually write this recursively. So we can write this construction just using standard Gaussian sequential updating. So there's nothing terribly novel or interesting about that. But what is useful is that it then allows us to obtain a proof of consistency of this actual scheme here, right? That as n tends to infinity, the covariance parameters tend to 0, then this construction would basically coincide with what we would obtain from a deterministic integration scheme. And this is just a little picture, a little cartoon of what is going on. Here's our initial condition. So this is the derivatives, right? We then, given this particular point here, we can integrate it probabilistically, and we can then obtain another step forward or step backward sample of a realization of the state value. We can then transform this deterministically via the system of equations back into the derivative space. We then use the linear projection to do this integration and prediction and so forth. So that's for a very simple initial value problem. As I said, for PDEs, it holds as well. So now what we've got is a measure on the actual solution, P of u given t, and this skeleton solution over the discrete grid. What, of course, we would like is this posterior over theta, or parameters and variables of interest, the actual function at, say, the time points associated with our data, given our data. And it turns out that we can obtain a very simple MCMC scheme where we can propose our random variables just through some proposal distribution, and then we can sample a probabilistic realization of the state. So we propose a u prime at the time points that we've observed the data from, conditioned on these theta primes. And because we're using this as a proposal distribution, so if you remember, I go way back here, so we're using this, which is conditional on an which is joint with an f as well, as the proposal mechanism. Then of course these cancel out in the numerator and denominator, and the acceptance ratio is something that can be computed and allows us to sample directly from this posterior here. And that's pretty much the whole scheme. So the 2 points are that we have a means of probabilistically sampling solutions, if you will, or functions which are consistent with the system of equations, and that construction is consistent in the same sense as any classical numerical integrator, but we obtain a measure of uncertainty associated with the discrete form of that construction. And so what we can now then do is obtain realizations from this posterior of the parameters of interest if we want to calibrate the model, but also realizations of the system as well. And here's an example. So this is just standard heat equation. So I've used this because one, it's a PDE, and two, because we've got an analytic solution that we can actually compare against. And so this is just a very standard heat equation with boundary conditions where the values at the spatial extremes are held fixed at 0. We have an initial functional at time 0, which is just some sort of sine function, and then we just let the temperature diffuse through time. And so here what you can see at each of these time slices, the green value is the actual analytic solution of the PDE. And then the red and the blue values are these probabilistic realizations and of the solution. And the error bars indicate the posterior predictive variance at each of these spatial locations here. And what you can see, hopefully, is that the blue realization is based on a coarser grid than the red realization. So this is nice. It shows the consistency of the scheme in operation for, albeit a very simple PDE. But I think I want to show you something further where we now are going to have a global parameter of the diffusion constant here. So unlike Kennedy and O'Hagan, there is no model error mismatch. Right? So the model matches the actual data generating process exactly. So the only uncertainty is caused by induced by the actual discretization. So we're going to assume that we don't know what the diffusion coefficient is. So we want to get a posterior over that. So we get the marginal posterior over that. So if I use a very coarse 8 by 25 grid, so 8 spatial, the grid is in the one-dimensional spatial representation is gridded up into 8 sections and then temporally 25 sections. And you should pay attention to this particular graph here. So the generating value, kappa, is equal to 1. And so if we use the actual analytic solution, then clearly we're going to get a nice posterior centered around the generating value, and you can see it's fairly confident. But if we don't use the analytic solution and we use just a standard integrator for this PDE, and we plug that into the likelihood and ignore the uncertainty induced by this mesh, then we get a posterior that looks like this. So it's biased and it's highly confident. So the posterior doesn't even really cover what the actual generating value was. So even for this very simple example here, we can immediately see this sort of bias, which is something that is difficult to assess if we were relying on bounds on errors and so forth. And if we didn't have massive amounts of computing power. So if we scaled this up to a much larger mathematical model, then this becomes quite problematic. On the other hand, the posterior obtained by, so the marginal posterior obtained by this probabilistic construction, which I just described, well, you can see that for the same grid, the same refinement of the grid as we would obtain here. We now have something which is, well, at least, you know, if you look at the scales here, you can see that the level of uncertainty is far higher, but it's a kind of coherent, you know, we could do coherent inference here because, you know, the true value is, the generating value is certainly within the sort of region of mass. And as we refine the grid, then the posterior uncertainty starts to shrink in a consistent manner. So this is all good. You know, this kind of proves the concept and proves the methodology. Oh, it's 11 o'clock I finish, or 10, yeah, I'm just done. So this is great. Let's now just look at a whole load of examples just to give you an illustration. Here again is another very simple system of ODEs. It's the Lorentz 63 system, which was used to study sort of the effects of long-term prediction of chaotic systems like weather. And what I'm going to show you is a number of these realizations, so samples of the solutions drawn from this posterior measure. And so here are 100 realizations where we've kept the mesh, the time discretization fixed, and we've also kept the initial conditions fixed. And despite that, just due to the chaotic attractors, then the repeated sampling from this posterior starts to capture the fact that that this is indeed a chaotic system, and coherence starts to get lost as time progresses. Now this is something that we get for free with this construction here. If we wanted to do this numerically, we would then have to do Monte Carlo simulations by randomly perturbing the initial conditions or the actual width of the actual mesh itself. So this is quite useful and suggests that this probabilistic construction may well be useful for these sorts of systems, but it's not something that we've really looked at. You all know Navier-Stokes equations. So again, this is just a very simple example, 2D on a torus. And again, what I'm going to show you are, I'll just cut to the chase. So these are 6 realizations. So 6 realizations drawn from that posterior measure. And of course, because this is now spatio-temporal, these are the actual objects that we are able to sample. Probably this is good to watch on a Friday night after a bottle of wine, because you can then start to see sort of deviations as time progresses. And in fact, on my website, I have an example with very turbulence has got a very high Reynolds number. So we've got solutions for Navier-Stokes where the Reynolds numbers are very high, and you can actually see the differences as time progresses of realizations of these functions from drawn from this posterior. Again, here's another system, Kuramoto-Stevashinsky, that again, this is used to model flame fronts, for example. So we have one spatial dimension and time, and again, if I just look at all of these draws from the posterior measure, you can see that there is variability there caused by the sort of chaotic nature of that system. And just because of time, one of the nice things about this construction is that I'm working with some engineers and geophysicists who are doing Bayesian inference on very large scale inverse problems associated with large PDEs describing ice sheet flow and subsurface flow. And they're very keen to use these Riemannian manifold Hamiltonian Monte Carlo methods, but they are excruciatingly difficult to use because to obtain the metric tensor, we have to solve two adjoint systems. And then to get the derivatives of the metric tensor, the components of the connection, we require another two adjoint solves. And this just becomes completely infeasible. But with this construction here, we can actually define a metric tensor, right, based on the conditional posterior of the solution, where now, in essence, all that we require to do is have that one solution, and we can then, rather than having to solve the sensitivity systems or get the second using a joint system, we only need one solve. So rather than requiring 4 PDE solves, we only require one probabilistic solve to define the metric tensor and the components of the connection. So this is quite exciting because it's now allowing these engineers to look at large-scale inverse problems and use these MCMC schemes, which really exploit the underlying structure in the systems of equations. But that's another thing. Okay, so here's the sort of big example. And this is a biochemical pathway that describes the production of 4 proteins, and I've just called them U, based on stimulation at the cell surface by a particular drug, and this is EPO. How many of you have heard of EPO? A few of you. So I gave this presentation in Texas, in Austin, Texas, and I made a joke about a very famous resident of Austin, Texas, being familiar with this, but it didn't go down terribly well. But I can see some of you appreciate that joke. But in any case, so what we have here is a coupled nonlinear system of differential equations that are also time delayed. And so what we want to do now is obtain the posterior over all of these kinetic rates. I should also point out that the observation process is such that there's a nonlinear transformation, so we can't measure the each of the individual activated proteins. The technology is such that we can only measure the total amount, the total density of certain combinations of the active and inactive proteins. So we have this nonlinear observation model. Anyway, to cut a long story short, here are samples drawn from the marginal posterior of the actual solutions of the proteins. This is the data here. And these are the sort of marginal posteriors of all of the parameters. I won't go into detail about what these mean, but this is actually quite an exciting study. But anyway, let me close by saying that I've attempted to address the issue of the representation of a mathematical model in terms of a discrete mesh solution, and tried to account for that in a probabilistic sense. And in essence, all that we've done really is that we've defined a measure over the functions that are consistent with the system of equations and boundary values and so forth. And we can now account for this inflation of uncertainty because we're using discrete solutions, and we can assess it in a formal way. And we can use this to ask questions about, when do we have to refine the mesh, or could we get away with using a coarser mesh and still obtain coherent statistical inference? And so we have this Monte Carlo solution, which for PDEs and ODEs, and it gives a global solution. So this isn't like Feynman-Kac, which would give local solutions. And so the sort of things that we're looking at are exploiting things like experiment design to adaptively discretize the meshes. This gives us a consistent estimate, and Andrew Stewart is now looking at some formal analysis, certainly for PDE systems of this scheme here. And that's us. So what we've tried to do is that the discretization, the solution, and uncertainty quantification, we've tried to unify it in a common inferential framework based on Kennedy and O'Hagan's scheme. And that's it. There is a paper on archive, and there's a nice website with all of the code to replicate everything. It's reasonably well documented, and you can download it, you can play with it, and there's even a video with some Pink Floyd music. So yeah, I mean, so if this did interest you, please download the paper, and I'd love to hear any critical comments, and play with the codes, and if they break, then I'd be interested to hear about it.
Questions?
Can you comment on how the computation, first of all, is the main computational bottleneck the PD-OD calculations, or is it the inversion of matrices and so on for the guessing?
So that's a great question. That's something I didn't mention. So the key thing here is that, in essence, all that we're doing is solving linear systems. You know, so in getting the posterior mean and the covariance structures, we're just having to solve these linear systems, and that scaling is no different from Crank-Nicholson or what have you, where you use conjugate gradients and so forth. So the computational scaling of both standard PDEs solvers and this scheme here are the same. But our implementations don't have the advantage of 50 years of software development and engineering design to give us very efficient codes. But I think the fact that the order of scaling is basically gated by solving a linear system, as is the case with PDEs, then it gives motivation to actually invest some effort, some software design engineering effort to develop these codes. So the bottleneck is the same as it is for PDEs. There's no additional computation cost.
Sorry, Mark, just a clarification. Do you completely dispense with the ODE solver?
Right, so that's another very good question. And in the presentation here, I basically completely dispensed with it. But the very first thing that you can see here is that there's no reason why we couldn't use a PDE, a solver, either as a skeleton, which we can then use this to refine or not. It's something that we discuss in the paper, and certainly for the work that I'm doing with these engineers who are desperate to use Riemannian manifold HMC, then that's exactly what we do. We just use a standard PDE solver and plug it into this construction here. So the answer is, if you want, you can use it, and I think that there's further development work in for example, for multi-scale systems where you could use an initial PDE solver, deterministic one, and then use this construction here to refine, interpolate between the actual grid points. Did that answer your question? Yeah. My co-authors were just dead keen that this was fully probabilistic. So I got beaten down and wasn't allowed to say that, yeah, you could just use this, the output of a standard solver to define this conditional measure. And of course, if you do that, then the measure on this is this is deterministic. And so, the conditional distribution would just be this Gaussian measure.
Do you learn the kernel parameters?
Yes, yes. And I have to say that's the difficult, as we know.
Kernel parameters are these alphas and betas.
Yes, yes.
So for the Navier-Stokes, for the 2D Navier-Stokes, what are they?
We actually fixed those. We couldn't. It was a massive job just getting 2D Navier-Stokes. So we just fixed them based on the actual discrete grid. So as you were saying, you know, A and B is just going to be the actual width of the elements themselves. So there's still a lot of work that needs to be done in terms of, you know, so all that we've done here is we've defined this this MCMC scheme, which is hardly the most efficient, but it's one that is useful. So there's still a lot of work, very interesting work that needs to be done to see how we could actually estimate these parameters more efficiently.
So do you have any result like for asymptotic consistency?
Yeah, that we've got it there. So that is
I mean like Berkshire-Normlitz type result. I mean,
sorry,
when I mean consistency, I mean in the sense that you are sure to converge towards the true
yes,
solution.
yes,
So you got that.
we've got that.
Well,
It's
it
in the
must
appendix.
depend on the parameters of the kernel, no?
Yes, but and that consistency. So those as the consistency is as you would expect. You know, as n the mesh size tends to 0, and as the kernel, so the kernel parameters would then also tend to 0. And it's a kind of obvious result. But we have the asymptotic consistency.
It's only for the prior, not for the posterior.
No, it's for the posterior.
It's for the posterior.
Yes. I mean, it's a bit strange to talk about a posterior in the absence of data for the solutions of the systems. I mean, the proof of consistency is, you know, it follows Euler. It's not. But Andrew Stewart is very interested in looking at this to more formally look at this from PDEs. So I mean, all that we've done is very naively just used this scheme and extended it to PDE systems. But there's a whole load of analysis that needs to be done to, you know, establish consistency for certain classes of PDEs and so forth. But I think as a working tool for engineers, physicists, people that are actually modelling large-scale systems, and looking at inverse problems and really needing to quantify that uncertainty. At least we have, you know, this provides a coherent framework to propagate those sources of uncertainty. And the key thing is that, you know, if the system is so simple that the discretization error is negligible, then you see that in the posterior. And at least you know, okay, we don't need to worry about the discretization error. But it would also flag up if, you know, the discretization error is dangerously high because of too coarse a mesh. Then we have, you know, that is propagated in our posterior inference. So I think accounting for this is important. And doing it statistically rather than working with error bounds, we then have the full probabilistic semantics.